Hi everyone, this is André. As of January 1st, 2026, Flow5 is an open source application, and I'm taking this opportunity to remake this whole video playlist. The goal here will not be to make a tutorial video. Instead, what I want to do is try to share those best practices that will help you make best use of Flow5. Well, in Flow5 everything starts with airfoils, so I've already defined a NACA 9 airfoil. Let's switch to the design view here, and the first thing you need to do once you've loaded an airfoil is repanel it. So let's use the menu option here, active foil, repanel, same as in XFNR5, use something like 100 to 150 panels. And use this slider here, which is new. The reason being that Flow5 now uses its own set of geometry modification routines instead of using those from the GDES module in Xfoil. So we use the slider here to increase or to smooth out the paneling, to increase the density at the trailing edge and at the leading edge, and also keeping some reasonable density on the top and bottom surfaces so that Xfoil can calculate the transition from laminar to turbulent. Alright, let's save this. I'll overwrite each time to avoid overcrowding the population of airfoils. Next thing that you need to do once you've defined an airfoil is to set its trailing edge flap, if there is to be any, which should be the case more often than not. So what we do here, the active foil, we set a flap. Now things have changed somewhat in Flow5 compared to XFNR5 and compared to the previous earlier versions of Flow5. We can still set a trailing edge flap by activating the box here, and this will define the hinge, here in this case at 70% chord and half thickness. And this hinge remains a property of the airfoil, which makes sense in the physical world. It belongs to the airfoil. However, the flap angle defined here downwards is no longer a property of the airfoil as it used to be in XFNR5. It's now a property of the polar. The flap angle has been moved to the polar. It's displayed here for information only, unless I make the deflection permanent. And this would switch back to the XFNR5 mode, the way we used to work in XFNR5, where this grey airfoil would become just another airfoil to be used for the design. This can still be a good way to work. However, it's no longer the recommended way to work. The recommended way is to leave the trailing edge hinge as part of the airfoil and to move the trailing edge flap angle to the polar. Well, let's see how it works. So I'll save this, I'll overwrite it, and as you can see, the trailing edge flap deflection has been cancelled or discarded. It will only be used and displayed when we define the polar. Let's continue. We will need another airfoil for the main wing. This one will be used for the tail. So let's load this second one from a file, and I will load it. I will use the good old Epler 174 here. There it is. Let's give it another color. Let's make this one blue and let's make this one green. Okay. And lastly, let's give it a simpler name for clarity. It will be the E174. Okay. Same thing here in the case of the Epler foil. We need to repanel it, and the airfoils of the Epler series are known to have a very coarse paneling, so this is twice as important to here in this case. So again, something like 150 panels and a smooth paneling. Okay, save, overwrite, define the trailing edge flap. Here we go, trailing edge flap. I'll leave it at the same location. Note that if on the wing the hinge is located at 70% chord at some span location and 80%, let's say, at another span location, you will need to define two airfoils. But for simplicity, I'll just be using one with hinge located at 70% chord. I'll save this, overwrite again, and the two airfoils are now ready for calculation. Let's switch to the polar view for the calculations. Let's select the airfoil we are interested in, and let's define an analysis. F6 is a shortcut. What do we see here? Well, we have 5 types of polars. The first 4 are common to XFLR5, and type 6 is new. Type 1, 2 and 3 are inherited from Xfoil. So if you're not familiar with these types of polar, I recommend that you read the Xfoil documentation. Let's have a look at them one by one. Type 1 is the simplest or classic type of polar, where the main variable is the angle of attack, and because it's a variable, which we will define later in these tables here, it's disabled. The parameters which can be set are the Reynolds number. Let's enter 100,000 Reynolds number, the Mach number, the transition parameters, which I will set now with the trip location at the trailing edge, and lastly the trailing edge flap angle, which is new. If you are not familiar with the transition parameters, please look up the Xfoil documentation where they are explained in detail. So let's run with a simple type 1 to start with. And we'll run with the default parameters which are here. So let's click OK. I'll keep the ranges which I have predefined and launch the calculation. Alright, what do we see here? Well, the way Flow5 does it is it proceeds by ranges. And why is that? Well, it's because Xfoil calculates solutions incrementally. It starts with a solution and uses the boundary layer calculated for this solution as the starting point for the next calculation. So this makes Xfoil converge more often and faster. So it makes sense to, for one, start at an operating point where Xfoil is most likely to succeed, and usually this is around 0 degrees. And to proceed incrementally with small increments, typically 0.25 degrees or 0.5 degrees. What do we see here? Well, Xfoil converged up to 6.5 degrees, at which point it failed to converge. Flow5 therefore forced the reinitialization of the boundary layer, and Xfoil continued from that point on successfully. It moved on to the second range. Each time a range is selected, Flow5 reinitializes the boundary layer, because usually the last converged solution is very different from the next one, and reinitializes the boundary layer each time the Xfoil does not converge. And that is it. And there is our polar. Let's define another one. Type 2 and type 3 I don't use, so I'll skip. Let's select a type 4 and let's keep angle of attack 0 degrees, flap angle 0 degrees, and parameters, transition parameters unchanged. Let's save this. I've got some predefined ranges here which I will just keep and run the calculation. Right, the window disappeared, which means there weren't any errors. If you want to see it again, you can type analysis and open the analysis window, or type L to view the log file, which is the same thing. Right, let's give this polar another color, whatever, and hide the type 1. Well, we see that our polar is here with a strange behavior we'll investigate later here. And it displays as a vertical curve on the alpha graphs, which makes sense because all these operating points, or all the values of the polar, have been calculated for the same angle of attack. So we have an option here to help us with that. Let's call this set of variable graphs alpha. And what I'll do is I'll define another one which I will call Reynolds. Oops. There we are. And once I make sure this Reynolds set is selected, I will change the variables to Reynolds number on the x-axis of all the last 4 graphs. Which the point is that you can switch between variable sets without having to change the variables of each graph individually. Alright, and finally let's define a type 6 polar, so F6. Let's define a type 6. Let's define it this time, let's say, for angle of attack 3 degrees. And parameters here unchanged. And this time, theta, the trailing edge flap angle, is the main variable of the calculation. So we can save this. Our polar is ready. Let's give it again another color. Pink is fine. Define some ranges, again starting from an operating point where airfoil is most likely to succeed, and calculate. Everything went fine. Let's hide the type 4s so that we can focus on the type 6 polar. Again, the Reynolds number or the angle of attack are not the main variables we are interested in for this type of polar. So we define a third set, which we call theta. And we can change the variable on the x-axis, in this case, to theta, which will, and this set of graphs will be the preferred set to visualize type 6 polars. Right, let's carry on. Let's have a look at this type 1 polar, and let's imagine that we want to do the same calculation but with the flap angle down, let's say by 5 degrees. So what we will do is enter a positive trailing edge flap angle. The name will change, should change, theta 5, okay, and let's define another one, F6, this time for -7 degrees. Okay. And here is our third polar. I'll change the symbol. Since the trailing edge flap angle is upwards, I'll use triangles pointing upwards, and this one, flap down, triangles pointing downwards. And run the calculation again for each. Okay, number 1, close, and number 2, alright, and let's switch back to the alpha display. Let's show this type 1, hide the type 6, and I'll zoom in on the second graph by typing 2 on my keyboard. Second graph. Well, our polar here with the non-deflected flap, trailing edge flap is in the middle. When the flaps are up, triangle upwards, we have less lift, and we have more lift when the flap is downwards, which makes physical sense. Okay, let's finally imagine that we want to run these same 3 calculations for the neck and eye. We could define the same analysis one by one, or we can define them all at once by duplicating some existing analysis. So select the neck and eye, duplicate the existing analyses, select those that you want to duplicate, click OK, and there they are. By the way, you will often hear talk about polars and analysis interchangeably. The reason is that they are the same object. The analysis, usually when I talk about the analysis, I mean the input parameters, the settings. And when I talk about the polar, I mean the results or the curves. The reason is that these terms refer to the same underlying object in Flow5. So polars, analyses are the same thing. Okay, and we could run these calculations, these polars one by one, but we can use the new batch mode, which has been added to Flow5, where we select all the polars we are interested in, select the ranges of type 1, 2, and 3, type 4, and type 6. So in this case, type 1, I'll be interested in these 2 ranges, and type calculate. So this will may take a few seconds, hopefully not too long. For the Necker 9, no, that's fine. Close. And here are our 3 green curves for the Necker 9 with less lift as expected than for the Epler 174. Alright, let's display all the graphs. I'm interested in type 4 polars for the next part of the demonstration, so I'll type T4 here, and it selects only the type 4 polars available in the database for display. You can click on the curve, it will automatically select the type 4, and what I would like to do now is investigate this strange behavior to understand what's going on. What I'll do is open this graph in a new window, keep it above others. Well, it's already the case by default, so that's fine. Move it to somewhere on the screen and switch back to the operating point view. And lastly, I'll run this calculation again, but this time storing the operating points. Alright, here they are. And finally, let's investigate this this behavior here. I'm trying to get everything on the screen. Right, boundary layer displacement, D star. Let's select the first operating point. Now, there is a double filter applied here, which may be a bit confusing. If this checkbox on the bottom right is activated, only the selected operating point will be displayed, providing it's also enabled, its visibility is also enabled by activating the little cross on the right. So there are 2 filters applied, which may be a bit confusing. But anyway, let's select the first. And when we select the operating point in this case, it is also highlighted here in the graph. It's the point at lowest Reynolds number where the drag is maximum and the lift is low. I'll try to put this somewhere where it's okay. Okay, anyway, here. Let's move down the operating points, increasing the Reynolds number, and watch for this red dot here, this red square, which will move along the curve up to this point. So at this point we have a very thick boundary layer. I suppose it's fully laminar at low Reynolds number. Let's increase the Reynolds number progressively, and we can see this boundary layer thickness which starts to decrease until we reach the point where the behavior on the polar curve changes. So that's roughly 40,000 Reynolds number. And from that point on, we should see the boundary layer reattach much faster with the creation of a laminar bubble. Let's have a look. So yeah, the behavior changes, the Reynolds number increases very fast, and we can see the laminar bubble appearing, showing up on the airfoil with a turbulent behavior downstream of the bubble. And there we go. And we can see at this point that we've reached sort of a steady state. We're still with a laminar bubble, which is slowly decreasing in thickness. Anyway, there is our operating point view. What else is there to say? If you are interested in the boundary layer, this is the view here with the velocity at the edge of the boundary layer, UE, the D star, which is the displacement thickness, theta, which is the momentum thickness and not the trailing edge angle on this graph, and H, which is the shape factor, if I remember correctly, which is the ratio of the momentum and displacement thickness. The only thing to mention here is that these results, these boundary layer curves or data, are not stored in the project file. They must be calculated on the fly. Alright, and lastly, the design view. I think we've already talked about that one. Just a few shortcuts that may come in handy. If you double click on a view anywhere in Flow 5, it usually centers on that view. If you are using a laptop without a mouse wheel, you can type or press the Alt key on your keyboard and move the mouse to zoom in or out. And what else? If you press Y on the keyboard and use the mouse wheel, it will zoom only on the Y axis. These are things which should be common to all Flow 5 views, including graphs. Alright, there's a lot more to say and a lot more to explore, but I just want to keep those videos short. Yep, sorry, still one thing that should be mentioned. If I switch back to the polar view, hide this type 4, there is this batch mode, which is called here the legacy mode, but maybe that's a wrong term. This is the mode that we use to generate the viscous data that will be needed later on in 3D. So the way we do it, we select the airfoils we are interested in, let's say the Necker 9, select those polars which cover the flight envelope needed later in type 3, select our parameters here, the ranges, and launch the calculation. Just before I do that, one additional option which was not there in XFLR5 or in the first versions of Flow 5, well, Flow 5 did, the early versions did not have Xfoil anyway. This option here, if we activate it, will force the transition from laminar to turbulent at the hinge location. This is a judgment call which you are free to make or not. Let's say that I believe that the surface discontinuity in the case of an airfoil, depending of course of how this hinge is made, may force the transition from laminar to turbulent. It's the equivalent of a turbulator or the dimples on the golf ball. The idea here is that forcing the transition from laminar to turbulent using either this option or the transition parameters here will help Xfoil to converge significantly. So whether you deem that this transition occurs or not is yours to make. In the present case, I will just deactivate it and create the polar mesh. Now this polar mesh has raised many questions, rightly so, because it's a bit confusing. If you're not familiar with the way it works and the way it is used, please look up the video I made in the XFLR5 playlist or read the documentation on the XFLR5 webpage to understand again how it works. The idea here is that instead of calculating the viscous drag each time in the 3D analysis, it just interpolates its data on this set of curves here. Now, one thing which is important to mention, this used to be a mandatory step in XFLR5 to run 3D viscous calculations. It is no longer a mandatory step now in Flow 5. It can still be the best way to do it. However, there is now an option in the 3D plane design module where we can calculate Xfoil viscous data on the fly, and I'll explain how to do it when it comes to that. So this is still a good way to do it, and often it is the best way to do it. It is no longer a mandatory step. Alright, I'll end this video here, and next up I will be talking about plane calculations, plane design and calculations.